Yes. Oh, yeah.
Welcome to the November talk for the Portsmouth and District Physical Society. Tonight's speaker is Professor Hendry from the University of Glasgow. Professor Hendry is Professor of Gravitational Astrophysics and Cosmology at the Institute of Gravitational Research there. And he's a member of the LIGO Scientific Collaboration, which, as you know, was involved in the recent discovered gravitational waves recently. His main interest is in multi-messenger astronomy, and he's a fellow of the Royal Society of Edinburgh and the Institute of Physics, and he's currently chair of the Institute of Physics in Scotland. His talk tonight is called Listen to Einstein's Universe with Gravitational Waves. I'd like to welcome Professor Hendry.
Good evening, everyone. It's a great pleasure to be with you here in Portsmouth. And several of my former students and colleagues have worked at the Institute for Cosmology and Gravitation here, so I've been a frequent visitor over the years, and was delighted to accept this invitation to come along and to, I'm being assisted, a bit loud, yeah. Again, 20 years experience filling vast lecture theatres without the help of a microphone means that there shouldn't be any danger of me falling asleep. I think I'm often told that that would be rather loud, but as we will learn in the course of the talk, one of the common themes in gravitational wave astronomy is dealing with a lot of background noise. So we'll come back to that point one or two times. Right, okay. Does that sound about right? I mean, to be honest, I'm much happier without the microphone altogether, because that's what I'm used to. But again, if it's important for recording, then I'll stick with it.
Stick with it.
Yeah. Sure. It's just that I think there may be a tendency for me to forget that I don't have to use just my own voice to fill the room, and that may mean that I'm rather deafening the people in the front, but I'll do my best to remember. Right, okay. Right, where was I? Can I start again, please? Right, hello everyone. Thank you very much for coming along to this lecture. It's a great pleasure to be with you and to be accepting an invitation to come and talk to the Physical Society. As I said, I've been a frequent visitor to the ICG, and it's always a pleasure to be able to spend time talking to them about some of the latest discoveries in cosmology and astrophysics. And I suppose they don't come much bigger than this latest discovery, which, as Edith said in her introduction, has been all over the news for the last about a year and a half. And what I want to do tonight is to give you some of the background on how we made this discovery, but also to look a little bit ahead at some of the excitement that maybe lies in store in the future as we open up this new way of looking at the universe and perhaps make even more exciting discoveries in the years to come. So before we do any of that, we've got to try and address some more fundamental questions. What are gravitational waves, and why do we think they exist, and how do we detect them? So gravitational waves, to answer the question as to what they are and how we detect them, we've really got to step back a little bit and ask some questions about gravity itself. So gravity, as a concept within physics, has been around for quite a few hundred years, and indeed as a concept in everyday life has been around for as long as there's been people on the planet, because it's what keeps our feet in the ground. We know that when you drop something, it falls to the ground, and it speeds up as it drops. Even that is a relatively recent deduction in the early years of the work of people like Galileo and Isaac Newton. We developed a quantitative understanding of how objects fall in the Earth's gravitational field. And that helped Isaac Newton, leaving aside the others who were involved, but just focusing on Newton, it helped Newton to formulate a picture of gravity as a force. And that means every massive object in the universe, according to Newton's way of thinking, attracts every other massive object with a gravitational force that's proportional to the masses of those objects, and also depends on how far apart they are. So within the framework of Newton's description of gravity, it's possible to understand pretty well how the Earth orbits the Sun, or the Moon orbits the Earth, or indeed to send astronauts to the Moon and back to work out the trajectory they need to follow to get there and to be safely returned. But there were some philosophical issues with that way of thinking about gravity, which attracted the attention of none other than Albert Einstein in the early years of the 20th century. And Einstein had some problems with the notion that gravity could act instantaneously from one point in space to another. Or another way of thinking about it would be to say, how does the moon know that it's supposed to orbit the Earth? So what Einstein developed was a picture of gravity that was fundamentally different. It approached gravity, his theory, which we call general relativity, not as a force, but as a curving of space and time. And the conventional picture that we often use, and maybe many of you have seen this picture used in this context before, is to think of a stretched sheet of rubber, a bit like a trampoline. And that means, if we consider the Earth sitting in a trampoline, I would have brought one along, but I don't think EasyJet would like me rolling up at the airport with a portable trampoline to bring along to my talk. But we quite often use this in practical demonstrations of what we mean. You have a massive object bending the trampoline, and that means that other objects will follow a curved path around its vicinity. So I've just got a picture for you tonight instead of the real thing. And if we imagine the Earth sitting in a trampoline, a bit like shown here, then we can see that as the moon orbits the Earth, one can think of it not so much as the moon feeling a force reaching out from the Earth to the moon, but instead the moon just experiencing the local curving of the space-time that's being warped by the mass of the Earth. So there's a neat little phrase attributed to John Wheeler that tries to capture this. It says, space-time tells matter how to move, and matter tells space-time how to curve. And many of you might have heard that before too. And the idea there is that it's the presence of the matter and indeed energy in the universe that creates the space-time curvature, and then other matter will respond to that space-time curvature by following a path that's determined by that space-time curvature. So all of that gets us a long way in understanding the key principles in Einstein's general theory of relativity. But it doesn't quite get us to the point of having gravitational waves, because for that, what we need to do is to make the trampoline wobble. We need to shake up space-time by accelerating those massive bodies. So when you have an object accelerating, the distribution of matter is changing. That will change the curvature, and the gravitational waves are essentially the ripples that spread out from that changing curvature in the gravitational field. So essentially then, gravitational waves are ripples in space and time caused by changing gravitational fields. And that means, when I wave my fist, strictly speaking, I'm producing gravitational waves, but because my fist doesn't weigh the same as a star, and because I'm not shaking it close to the speed of light, which is 300,000 kilometers per second, then the gravitational waves that I produce by doing this are unimaginably small. And if you want to maybe imagine just a little how small they are, then if one thinks of that rubber sheet again, there's ways in physics that we can characterize how bendy a surface is. Its tendency to bend, when it's put under, as Newton would call it, a certain force. We can describe that in terms of a quantity I'm sure many of you are familiar with, called Young's modulus. But the relevant physical quantities that would go into the calculation of Young's modulus for space-time, if we think of that bendy sheet of rubber again, well, it's not very bendy at all, because it involves the speed of light that I mentioned before, to the power 5, divided by Newton's constant of gravity, what people often call big G, which in the SI units that we use in physics is about 6 times 10 to the minus 11. So that's 3 times 10 to the 8 meters per second to the power 5 divided by 6 times 10 to the minus 11. That's a very, very big number. And it's that number, or variations of it, changing the powers slightly depending on the context, that will feed into the calculation of how stiff space-time is. So our notion of space-time as a bendy rubber sheet is a good analogy to give us a picture to hang the idea of space-time on and gravitational waves on. But the reality is, you've got to shake up space-time a great deal in order to produce any kind of measurable effect. And that's why me shaking my fist just won't cut it. We've got to look to the universe itself as a cosmic laboratory to shake up space-time enough to produce an effect that we might seek to measure. So what kind of events might produce a wobble in space-time that we could detect? Well, as we see in the little animation here, if you had two stars, two very dense stars and compact stars, like for example black holes, or as is represented here in cartoon form, neutron stars. Neutron stars are the remnants left behind when a massive star undergoes a supernova explosion. Well, that might just shake up space-time enough to be detectable. Because as they're orbiting around each other, and way faster in fact than shown in the animation, then the changing gravitational field, because of that accelerated orbital motion, might just give us a signal we could measure. But believe me, you don't want two neutron stars colliding in your backyard. So as those waves spread out through the universe, like ripples spreading across a pond, by the time they reach the Earth, they're going to be weaker. And that means the engineering and technological challenge we face is enormous. To detect the kinds of ripples that one might expect from two colliding neutron stars or black holes, one is talking about movements in our patch of space-time less than 1,000th the diameter of a proton, the particle that one finds in the nucleus of an atom. Or to put it in more everyday terms, if you take one of the hairs on your head, we're talking about 1 millionth the width of one of those hairs. So the engineering challenge to be able to develop detectors sensitive enough to measure those kinds of minute changes is fundamentally the reason why it took 100 years from Einstein's formulation of general relativity, which gives us the theoretical idea of gravitational waves, to them actually being measured in 2015 and then reported in February of 2016. But that's the story I'm here to tell you tonight. So how do we do it? Well, we do it using LIGO. Bearing the name on my sweatshirt here, it stands for Laser Interferometer Gravitational Wave Observatory. And I'm part of the LIGO collaboration. It's a vast collaboration. Well over 1,000 scientists and engineers continue to contribute to this vast effort. And indeed, there's another LIGO colleague in the room, Andy Lundgren, who's recently been appointed by the Institute of Cosmology and Gravitation. So if you've got any really hard questions, I can look to Andy to help answer them. And you know, the sum total of knowledge and expertise that resides in our collaboration, I continually find astounding. And of course, much of our life is ruled by telecons and email at all hours of the day and night, but it's astonishing, no matter how tricky the question, seemingly somebody around the collaboration will know the answer. And this isn't just the case now, it's been the case for decades. There's been many, many years of effort expended to get us to where we are now. So where are we now? Well, we've got these two LIGO detectors operating in the US, but in fact there's other detectors around the world as well. I'll come to that later, but let's focus on LIGO first. So these are two laser interferometers. They have this remarkable sensitivity that I referred to in the previous slide. One is in Livingston, Louisiana, the other is in Hanford, in Washington State. They're 3,000 kilometers apart at either end of the continental United States. And what on earth is a laser interferometer? Well, perhaps to this audience, it's a term that at least some of you have heard before, but many people would regard this as a very unfamiliar concept. In fact, the Scottish whisky company Bunnahabhain, some years ago, they had an advertising campaign that they called Great Unpronounceables of Our Time. And I think the rationale was that Bunnahabhain, you can see the word there, is one such example. I think I didn't pronounce it correctly, but then I've got 50 years experience of living in Scotland to get my pronunciation correct. So they used Michelson interferometer as an example of something that was unpronounceable, but actually to a physicist, this is quite common, to deal with this piece of equipment as a way of understanding a phenomenon that we see with light that we call interference. So what you see here is something very much like the Michelson interferometer that I would have used as an undergraduate student in Glasgow back in the mid-1980s. We've got slightly nicer ones now, but the LIGO interferometers are a lot bigger. The arms of the LIGO interferometers are 4 kilometres long. But the design principles are not so different, and that's really what I want to spend a couple of minutes focusing on. So what you want to do is to take a source of light, a laser, the L in LIGO, and to split that into 2 perpendicular beams. One goes one way, one goes the other. You bounce those beams off mirrors, you recombine them, and then you observe what comes out of the detector. And the idea is that when a gravitational wave goes by, it will stretch and squeeze space-time in such a way that when one arm is being lengthened, the other is being squeezed, it's being shrunk. So this represents, again in cartoon form, a gravitational wave coming out of the board towards you, but you don't need to duck. It's greatly exaggerated. If it was this easy to detect gravitational waves, we would have done it decades ago. Remember, a millionth the width of a human hair is all the sorts of size of effect that one is looking for. I've greatly exaggerated it so that we can get a better idea of what the pattern might be. So that's stretching and squeezing. When one arm lengthens, the other one is squeezed, and then vice versa. Students call this the LIGO dance. I don't think it will catch on, but that's basically the phenomenon. And as those laser beams undergo that periodic stretching and squeezing, then they'll move in and out of step with each other, out of phase with each other, we say in physics. And that means that you'll have either constructive or destructive interference, depending on whether the 2 laser beams line up or not. So what you're seeing in the cartoon, well, what I've done is I've kept one of them fixed. In reality, of course, both laser beams are going to be changing in phase, but just to show more clearly what the overall effect is, you can see that when they line up, you get constructive interference, they add together, and when they're out of step, then the signal can cancel out. But remember, 1 millionth the width of a human hair, that corresponds, even over those 4 kilometre long arms, to an incredibly tiny change in the path length, and that really fundamentally is why you need such large detectors. You need a whole bunch of other aspects of the technology that I won't really have time to discuss in detail, but let me just highlight 1 or 2. So firstly, those arms are maintained inside at a very, very high state of vacuum, about 1 billionth of an atmosphere more or less. And that's because even the odd stray air molecule could perturb the path of the laser enough to affect the pattern that one sees. So again, this is a similar video to the last one. It's just under our colleagues in Caltech, a bit fancier perhaps, but it's the same basic idea, and it emphasises that as a gravitational wave passes by, you get this change in the interference pattern. That's fundamentally what we're looking for. But the reason it's such a challenge is because, of course, many other things, many other phenomena could produce a similar effect, or indeed completely swamp this effect. So one way to describe all of that is in a diagram that looks rather complicated. So don't panic, we're not going to spend too long looking at this, but I think there's a few important points I hope to bring out from it. And one is that the name of the game here is about improving the sensitivity of your instrument. So that's to do with getting further down the vertical axis of this diagram. So the further down you are, the more sensitive you are to tiny, tiny changes. But what you see in this graph, series of graphs, is that there's a whole bunch of sources of what we call noise. Sources that would contaminate any signal from a gravitational wave spreading out through the universe, reaching the Earth, and preventing us from detecting it. And moreover, those noise sources depend on the frequency in which you're seeking to detect a signal. So the gravitational waves may well be out there in the universe at a vast range of frequencies, just like light. Electromagnetic radiation, light, comes to us from the cosmos across frequencies ranging from the very, very small to the very, very large. why should gravitational waves be any different? But, crucially, if you want to detect them down here on Earth, then there's only a narrow range of frequencies within which you have, to put it mildly, a cat's chance of doing so, because of the other sources of noise that would swamp such a gravitational wave signal. So essentially, it boils down to two competing factors. On the one hand, at low frequency, you're dominated by actually a bunch of different things, but let's just focus on the seismic noise. That's to do with the ground shaking. So if you're trying to detect a gravitational wave that's shaking space-time, you're trying to pick out that signal against the background of the Earth itself not being stable enough to allow you to do so. And then at higher frequency, the issue is to do with the instrument itself and to do with the fact that you're using a laser beam and there'll be fluctuations in the laser which may limit your ability to pick out such a signal. So there's a kind of sweet spot in the middle, around a few hundred hertz, a few hundred cycles per second, where the sensitivity is better. This is actually quite an old diagram, but I've kept it around from colleagues that I work with in Glasgow. I'll say more about that in a few minutes and what they've been doing for all of these years. But, you know, this is really what they've been devoting an entire career to doing, is finding ways to, if you like, keep the noise down and find ways to improve the sensitivity. And in fact, when I do schools outreach lectures, there's quite a neat way, I think, to illustrate that point. So I'm going to ask for your help in just a minute to explore, if you like, a different metaphor for keeping the noise down. Just before we do that, though, let's think about what the signal would look like. So remember those two orbiting neutron stars? Well, let's make them black holes now, because black holes are going to feature prominently in just a few minutes. And let's imagine that they're orbiting very close to each other, as we will see in this little animation. And if you can pick that out in the room, even from the back, there they are, there's one, there's the other. The gravitational waves are spreading out, and as they get closer together, the black holes eventually merge. But before that happened, we'll now loop the video so you can watch it again, you'll maybe see that they're spiraling ever faster around each other. So if we represent that as a graph, then it looks a bit like this. What you see is a pattern whereby the distortion due to the gravitational wave, first of all, grows in time, so the amplitude, to use the technical term, gets greater. That means the vertical extent of this pattern stretches, but also the frequency increases. That means that the cycles get closer together, they get more bunched up. And then the two black holes merge, and then space-time wobbles a bit more, and it settles down again. That's the phase you see here. So this is the result of a calculation done on a computer, and it's worth just keeping this in mind as we go on in a moment to think again about the instrument and all the huge advances that have made the detections possible. That what was also important were significant advances in our ability to simulate on a computer the signals that we were looking for. It really helps a lot if you know what you're supposed to be looking for. So we are looking for patterns like this, and we call this pattern a chirp, because it's got that characteristic rise in amplitude and frequency we see across here, and then it decays away. So we can look at it visually, but we can also think about it as a sound. That's why I called the talk Listening to Einstein's Universe. Gravitational waves are not sound waves, but we can think of them as sound waves, we can render them as sound waves, because the range of frequencies to which we are sensitive with our detectors on the ground, we saw in that complicated slide a moment ago, that range of frequencies from a few tens of hertz to a few hundred or 1,000 hertz or so, that's a range of frequencies that our ears can hear. So what would it sound like if you turned that pattern into sound? Well, the clue is kind of in the name. We call it a chirp. It would sound a bit like this. Like that. So a rise in frequency and getting louder as well. So my challenge to you, as I often do in schools talks, is to help me demonstrate the challenge that we faced in detecting chirps like this. So what I'm going to do for a moment is take off my microphone, if that would be cheating, and I'm going to invite all of you to make as much noise as you can. And I'm going to do the chirp sound, and I'll just keep doing it over and over again, and see if you can drown me out. I'm sure you can. I'm going to do this with year 7s or thereabouts. Really good at it. That's a challenge. See if you can drown me out more effectively than the last of year 7 science students. Okay, so I'll count back from 3. 3, 2, 1. Excellent, thank you. You're all honorary gravitational wave physicists now. And you did that very well because there was a wide range of different sounds that people made. Some people were banging on the table, some people were doing some rhubarb like you hear in the Houses of Commons. Some people were doing higher pitched, higher frequency sounds. And that's the challenge we've had, that we've had a range of different noise sources, like we saw in the complicated slide, many of which completely drown out the signal we're looking for. Now maybe some of you were lip reading, and you could see when I was doing the chirpy sound. And in a way that's quite relevant too, because later on, at the very end, I'm going to talk about not just listening to the universe, but seeing light as well. That's the end of the story. And I'm going to briefly describe some of the very recent discoveries that we reported just a few weeks ago. But for the moment, let's stick to listening to the universe and facing that challenge of picking out a signal when you've got overwhelming amounts of noise. So clearly, what you've got to do is try to improve the sensitivity of your detectors. We'll come to that in a moment. But another important strategy is to have more than one detector. So that's why there are 2 LIGO detectors. One of the reasons, believe me, it wasn't buy one, get one free, but this was a crucial part of the strategy in developing the technology, because it's one of your principal lines of defense to convince yourself that you've got a real signal from the cosmos and not some local source of noise if you see the signal manifested in both detectors. And indeed, Andy here, that's one of the areas that he leads on for LIGO, is the characterization of our detectors well enough so that we can do that job as effectively as possible. And it's really, really tough. I'm sure you'll all agree. But it's been crucial to have that deep understanding of what the noise ought to look like, but then crucially to have a kind of safety net, if you like, of being able to look at the data from multiple detectors. So as a gravitational wave from a faraway source washes over the Earth, we would be looking for a signal to be present in 2 or indeed more detectors. And indeed, this was a concept that was around for some years, because in the previous decade, from 2002 to 2010, we had a number of detectors operating around the world. There were the 2 LIGO detectors that we've heard about already, but there was also a facility which was given various names corresponding to the different stages in its development in Japan. But the 2 that I will focus on are Virgo in Italy with 3-kilometre arms, and also one in Germany. This was a UK-German project called Geo 600. So the 600 means 600 metres long, the arms, and that means that it wasn't as sensitive as the LIGO detectors in a very important respect, but nonetheless it was an opportunity to develop some technology that would later be a major part of changing LIGO into advanced LIGO, to upgrade LIGO to make it more sensitive. So that process began around 2010, and you can see from our collaboration web pages from then, in September 2010, that in fact my colleagues in Glasgow were called out specifically as part of that major effort to upgrade LIGO. So that's what I want to spend a few minutes on now. But I really would be completely remiss if I didn't own up from the outset to the fact that I was only just beginning to work in gravitational wave astronomy then, and as a humble astrophysicist I was looking on with awe at what they were proposing to do. So really, the hard questions related to this part of my talk, I'll do my best to answer if you have any, but the real experts are my colleagues that have been working hard on this for decades, up to the point where they could then implement some of those ideas to upgrade LIGO to advanced LIGO. So what exactly did they do? Well, the key idea was to get the noise down, like we said before. So that complicated curve with the yellow patch in the middle, if we represent that in a similar way, again, this is quite an old slide too, but it's part of our kind of history of how the field evolved, was the desire to go from a sensitivity that corresponded to the initial LIGO detectors that didn't detect anything, but to get that sensitivity roughly about 10 times better, 10 times lower down. So at higher frequencies, the focus in improving the sensitivity was to do with the lasers and using more powerful lasers. That was important as well, but the part that the UK mainly contributed to was at the low frequency end. And it was all about improving the sensitivity down about here by using heavier mirrors, what we call test masses. Suspending those mirrors had been a crucial part of the initial LIGO design, because that was to try and isolate them as much as possible from the local effects of the ground shaking. But what advanced LIGO brought to the party was a different way of doing that. Instead of using steel wires, using silica fibers, using glass fibers that were welded basically to the mirrors themselves, and then also looking at ways of improving the coating of the mirrors to again improve their performance. So all of this contributed at that low frequency end to getting us to a point where it was hoped that would be actually sensitive enough to make a detection. So there's a great deal more I could say about this, and again, you know, giving a talk in Britain, I don't always do this if I'm talking around the world, because it's absolutely a global effort. That's got to be acknowledged from the outset. But I think it's only fair in Britain to highlight the major contribution and the major commitment of the UK Research Council, STFC, in backing this part of the LIGO and Advanced LIGO project. Now, if you do want to learn a bit more about the engineering and the technology behind LIGO, I'll do my best to answer questions on it, but another good source is the LIGO magazine that we've been publishing for a number of years. So you can find those and indeed many other resources that I'll refer to shortly on our LIGO website. So I've contributed a few articles to the magazine over the years. In fact, I also came up with the idea of the LIGO puzzle page, including LIGO puzzles. These are just like Sudoku, but using the mathematical symbols of general relativity, so you can have a board as well. Anyway, it's about time we got into the astrophysics, so in the second half of my talk, I'm going to focus on that. The upgrade to advanced LIGO took a number of years, but by May 2015, the instruments were really ready to be handed back to, you know, the ongoing task of actually listening to the universe. And the plan was to begin the first observing run on September 18th. But actually, things were in good shape a little before then, a few days before. So the data gathering had already begun a bit before September 18th, and boy, were we glad that it had, because on September 14th, this is what happened. So let me pause that and talk to you a bit about what's going on there. Firstly, I'm cheating a little bit in two important respects. Firstly, I'm playing the file over and over again. So there's sound, and of course there's the visuals. And the repetition of the signal perhaps makes it a little easier to hear and indeed to see. So what we're looking for is that upward sweep in frequency and in amplitude. The amplitude gets greater, that makes it brighter. Remember, we called that a chirp. And again, if I stand a bit forward, it's easier for me to point that way. We see that chirp-like pattern in both of the detector outputs. The other thing that we're doing with the sound file, one of my colleagues in Glasgow first had a crack at this. is that we're shifting it in frequency upwards. And actually that's analogous to what astronomers often do when they make a false colour image of some astronomical object like a star or a galaxy. I think that also makes it a little easier to hear. So now, let me tell you what you're supposed to be listening for. As I play it again, maybe I'll turn the volume up if I can as well. Don't want volume mute. Maybe not. Maybe the challenge is more realistic if it's actually quite hard to hear, because after all, that's what this has all been about. But what you're listening for the first time is essentially a kind of low thud, which is at the end of this short burst of noise. And then when it's repeated at the higher pitch, the higher frequency, you hear it a bit more like the chirp sound that I was trying to produce before, and you were also effectively drowning me out. So that's what you're listening for. See if you can pick them out. So it repeats twice at the low frequency, and then twice at the higher, and then the whole thing repeats again. So that signal is the sound, if you like, using our metaphor of turning the gravitational waves into noise, into sound. The sound of two black holes colliding. And I was at a conference in China when this alert came to the attention of the collaboration, and it was amazingly exciting because, as you can almost see for yourself, it's a strong signal. And it did look very much like the real deal from early on in the process of trying to analyse that data. But it was a hugely difficult and time-consuming task to really convince ourselves that it was the real deal. And that deserves a whole talk in itself. The army of people that contributed to the effort to try and turn this putative signal into something that we could really hang our hat on and say, yeah, we have definitely detected gravitational waves, or at least couched in the language that we use in science, which is to attach a certain, what we call significance to the detection. So the amount of effort expended over those 5 months, from September 14th to February of 2016, at the time we were all saying, boy, life will never be that busy again. Well, it was. That was in August 2017, but we'll come to that a bit later. So a huge amount of effort to get us from this point to this point, which was the press conference that was held on February the 11th, 2016. And I'll just let our executive director, Dave Wrightson, from LIGO Lab, I'll let him say the immortal words.
Ladies and gentlemen, we have detected gravitational waves. We did it.
So how did we know that? Well, as I was saying a bit earlier, to try and set the foundations for this, one of the things that helped a lot was knowing the type of pattern we were looking for. And the analysis of the data allowed us not just after those 5 months to make the old claim that we detected gravitational waves, but also to say quite a lot about the sources that had produced them. So for example, our analysis led us to conclude that the sources that had produced that pattern, I've got it in my sweatshirt here, we'll see it again in a moment, those sources were massive stars. And in fact, really, almost you might say, surprisingly massive, more massive than we had perhaps first thought that we would detect with LIGO. So one of them was 36 times the mass of the Sun, with a certain uncertainty, with a degree of uncertainty that's represented by this sort of hill-type shape. The way that we represent our knowledge about the masses is in diagrams like shown. And then the other one, our best guess for its mass was 29 times the mass of the Sun. So 36 and 29, you can do the maths, add up to 65 times the mass of the Sun. So we were looking at two objects whose combined mass was about 65 times the mass of the Sun that merged together. We're pretty sure they're black holes, as sure as you can be of anything in the world of physics. Nobody was up there close to see them, or rather not see them, you might say, because of course you don't see black holes, because light doesn't escape from them. The movie on the left is a kind of imagining what it might have looked like if you could get up close to them, because the intense gravity from these two black holes as they orbit around each other on the death spiral would distort the light of background stars, a phenomenon that we call gravitational lensing. This has been known and observed, and is another important test of Einstein's theory of general relativity. So if you could have got up close and personal with those black holes, you would have seen some really quite amazing distortions of space-time produced by the intense gravity. But how did we come to the conclusion that they were black holes? Well, it's all to do with analysis of the pattern and extracting from that pattern the way that the frequency and the amplitude change allows you to estimate not just the masses, but also their distance. And then from that, you can get information on how far apart they were and how fast they were orbiting around each other. So, what about the distance? Let's look at that first. We've mentioned the masses. We'll look at how it all fits together. Our best guess for the distance was about 400 megaparsecs. A parsec is about 3¼ light years, the distance that light travels in light years, a light year. So 400 megaparsecs corresponds to about 1.3 billion light years. Another way of putting this is we were looking at something that happened a long time ago, far, far away. So remember, just said a moment ago that we could extract a lot of additional information beyond just establishing that it was a gravitational wave. So let's talk you through that. As I said, the way that the frequency changes, increases, the bunching up of the waveforms, and the way that the amplitude increases, that pattern gives us insight into the masses of the individual system, the individual objects in the system, but also how rapidly they're orbiting around each other. Because there's a relationship between the gravitational wave frequency and the orbital frequency. So that allows us to think about it maybe in terms of 3 phases. There's what we call the in-spiral, where they're just spiraling in. Astronomers don't always come up with the most imaginative names for things. Pretty much does what it says. The in-spiral phase, they're spiraling in towards each other. Then they merge. And then space-time wobbles for a bit. All settles down. We call that the ring down. That's the final phase. So, by analysing how that frequency evolves, like I said, we can relate that to the orbital frequency, and hence the speed of the two objects going around each other, and also their separation. And although all of this is done in the context of Einstein's theory of gravity, it's actually not that different from calculations that Johannes Kepler or Isaac Newton would have recognised. The part that needs Einstein is predicting the strength of the gravitational waves, but understanding the orbital behaviour of the stars bears a strong similarity to how we interpret, for example, the motion of planets around stars and so on. So all of that leads you to conclude that when these two objects of mass about 30 times that of the Sun were about to merge, they were orbiting each other with a speed close to more than half the speed of light, and their separation was only a few times what we call the Schwarzschild radius, which is the characteristic size of a black hole of a given mass. So all of that points to, let me put it this way, if they weren't black holes, they must have been something even weirder. Because how could you get such massive objects orbiting each other so close together and going around each other so fast, so many times per second, without them being black holes? So the chain of logic is really quite important, and in fact, both in the scientific paper that we published, and indeed also in a lot of the educational material that we created to support the announcement, we knew people were going to ask this question: how do you know they're black holes? So we thought a lot about making sure that that argument was really watertight. So here is a realization, done again in a supercomputer by our colleagues in the collaboration, of that picture of the stretchy rubber sheet. And remember, we established that it's really actually rather stiff, but here we've got objects that are so violent in their acceleration that they're shaking space-time a lot. And when the two black holes merge, let's run the video again, in fact, I was too busy nattering there, I should have paid attention to the big red spike that you're about to see, that's corresponding to the moment when the two black holes merge. And I guess a good way to think about that is a bit like taking a rubber band and stretching it until eventually it snaps and it releases a lot of energy. So this is the rubber band of space-time reorganizing itself as it goes from having two separate dimples corresponding to the two black holes into only having one. Now when that happens, it then rings down, and we did estimate the mass of the single black hole that was left behind, and we got our best guess there was only 62 solar masses. If you can remember from a few minutes ago, I said 29 and 36 were the masses before. So in about 0.2 of a second, the equivalent of 3 times the mass of the sun was converted into gravitational wave energy, represented in cartoon form by that big red spike that we saw in the movie. And Einstein, through his famous equation E equals mc squared, tells us how to relate that to a corresponding energy. And since it happened in about 0.2 of a second, we can also work out what it corresponds to as a power, which is energy divided by time. And it turns out to be about 50 times greater than the combined light power of every star in every galaxy in the entire universe. So that release of energy in a very short time as that burst of gravitational waves has a phenomenal amount of power. All the more so when you think that perhaps there was no light given off at all. Indeed, theory suggests that when black holes merge, it really is just the gravitational wave that's emitted. So in a sense, we're probing the dark side of the universe. And I think it was Darth Vader himself who said you should never underestimate the power of the dark side of the universe. And hopefully that little calculation I've just done will have convinced you that Darth Vader was probably right. I'm not going to argue with him anyway. So, all of this is of course in the framework of Einstein's general theory of relativity. But we'd like to test that as well. So this is a rather complicated looking slide again. I'm not going to dwell on this, but it will maybe sow some seeds for questions that people might want to ask. And the main thing I want to stress is that of course we're in the business of trying to test that theory, and so far Einstein's theory passes the test. So he looks quite happy. From this initial detection, GW 150914, we were already able to start the process of testing certain aspects of Einstein's theory, and indeed the subsequent detections that I'm going to mention in the next few minutes have allowed us to further refine that process. Let me turn next to the question of where the gravitational waves came from. I mentioned some minutes ago that the two detectors were 3,000 kilometers apart, and that means if gravitational waves travel at the speed of light, then along a straight line between the detectors, the light travel time, the gravitational wave travel time, should be about 1/100th of a second. But the gravitational waves, in general, might not follow that direction. They might come in from another angle altogether. And that means, if we remember our Pythagoras' theorem from high school, then we can use the delay time between the arrival of the signal at one detector and the other detector to say something about the properties of this right-angled triangle. Because basically a different part of the wavefront reaches Livingston from the part of the wavefront that reaches Hanford. And if you measure the delay time, it's giving you information not about the grey line, that's remember the hypotenuse you call that, but instead about this red perpendicular. So in fact, the delay time was about 7 milliseconds, and that allowed us to constrain this angle of the right angle triangle. But not very well, because what it really allowed us to do was to put out a map like this and to say to our astronomy colleagues, well, we think the gravitational waves came from somewhere in here, or maybe up here. And sadly, even the big banana on the bottom is about, if I remember rightly, 600 square degrees, which is about 2,000 times the area of the full moon. That's a big chunk of sky to go look in. But nonetheless, lots of astronomers around the world with whom we had a secret arrangement that they wouldn't spill the beans, but we would tell them that we had this alert. We subsequently, of course, convinced ourselves it really was a gravitational wave source, but we couldn't wait 5 months to tell the astronomers, so we told them at the time, and they went to look across this big patch of sky to see if they saw any electromagnetic radiation associated with the same spot. But, you know, that's a big ask, giving them 600 square degrees to search. So, no definitive signal was found, but maybe that's as expected for two black holes colliding. But this electromagnetic follow-up, as we call it, will re-enter our story in a few minutes in a very significant way. Let me just, before we get to any of that, just say a very few words about the broad impact of this detection, which frankly blew us all away. We just couldn't believe how much interest there was in this. In fact, myself and my colleague Joey Shapiro-Key from the collaboration, we were asked to write an article for Nature Physics, not about the science that we'd learned, but just about how we communicated that science to the public at large. So, more than 900 newspaper front pages on February 12th. We also had an extensive Twitter campaign with more than 70 million impressions. My daughter tells me that's an impressive number. And for example, the hashtags we selected were retweeted by all manner of people, including @POTUS, who at that point was Barack Obama. I'm afraid Mr. Trump hasn't shown very much interest in gravitational waves yet. Maybe that's a good thing. But one of our hashtags was Einstein was right. And remember that slide where Einstein was looking happy? Well, really what our hashtag should have been was Einstein isn't wrong yet. And that uses up too many of your 140 characters. So we stuck with this. But just we want to keep in mind that the reason we're doing all of this is not in a sense to prove that Einstein was right, but actually to test, to stress test general relativity and see whether it truly is a complete description of gravity. And indeed, in some sense, we already know that it isn't, because our strong suspicion is that quantum gravity is going to have a role to play in some level. But we're not there yet. We're not definitively making any statements about that yet. The proms in the Albert Hall, many of you might have been at those over the years. Well, I was greatly honoured to be asked to do a talk at the proms, not in the main auditorium, but in one of the side rooms, and it's because there was a piece of music on August 6th of last year called Gravitational Waves that was done in the proms that had been written by a Dutch composer. And then at the other end of the cultural spectrum, you might say, although I'm personally a fan of both, Sheldon was seen wearing the gravitational wave trace in the Big Bang Theory. Even more outlandish note, you can now get gravity wave real ale. I'm not on commission, but I just thought I would drop these in to mention all the ways in which we've affected the broader culture. You can of course get mugs and hats and pillows and t-shirts and all sorts of. Seriously, I'm really not on commission, but just, you know, a few weeks to Christmas, you can have a look at our website. You can even get a gravitational wave dress, which is, as you notice, a few people in our collaboration have worn it, and it looks very fetching. You can get a tie, so my wife got me one of those a few days ago for my birthday, which was great. I'm still waiting on the kilt, however. Gravitational wave tartan, I would be well in for that. On a more serious note, we've also been totally overwhelmed with the number of prizes that have come the way of the collaboration. Sometimes singling out key individuals, this is only right and proper. Other times awarded to the entire collaboration, and there's a whole range of them. Of course, I guess the most notable is the 2017 Nobel Prize awarded to Rainer Weiss, Barry Barish and Kip Thornton, and the ceremony to award that prize will take place in just a few weeks. But it's not all about that first detection. We've been doing lots more since. So in the final part, I want to give you a quick race through what else we've discovered, and just say a very few words about what might lie ahead. So firstly, there was a second confirmed detection of two merging black holes. This reached the Earth on Boxing Day 2015. So I made the fatal mistake that evening after our friends had gone off after a very nice dinner. I said to myself, I wonder if I had any emails today, and spent quite a lot of the rest of the evening watching it all unfold as indeed another event appeared to be detected. Now, this one was a little different though. It was in the detection band for more like a whole second rather than just a fraction of a second. And that meant that although it wasn't as strong a signal, if you remember the very clear pattern that one was seeing for the very first detection, we could kind of dig it out of the noise, helped by virtue of the fact that it was in the detection band for a longer time. Again, there's lots more I could say about this, but let me just, because there's so much more to cover, just mention that this was another pair of black holes, but slightly less massive. So again, it was just beginning to build up our picture of this population of these sources out there. And then LIGO resumed, well, first of all, it stopped taking data, but then there was a brief hiatus where the detectors were worked on to make further improvements and enhancements, and then it resumed operation on November 30th of 2016. And just a few weeks later, on January 4th, 2017, we detected another binary black hole merger, this time coming from what we call a redshift of about 0.2, which means an even greater distance than the first two sources. And this one was, unlike the Boxing Day one, again a bit more like the first. It was only in the detection band for a fraction of a second. I make a brief mention of another, which we didn't claim as a detection because we weren't sure, or not so sure, that it was a real event. But this was on the 12th of October 2015. So that one's just referred to as a LIGO-Virgo transient because we're not really sure it was a black hole, but it probably was a pair of black holes merging again. And all of this means that we're, as I say, building up this picture of the masses of these objects ranging from about 10 times the mass of the Sun up to 30 or more times the mass of the Sun. And then, of course, when they merge together, you've got an even more massive black hole. Right, I'm a bit behind schedule, but let me just spend a few minutes, and I'll be as brief as I can. Is another 5 minutes? Right, excellent, good. Let me skip that one to save time, because the really exciting stuff, I'm going to have to rush this. I'm so sorry I took a bit too long earlier, but it would be a real shame not to say something about what's been happening in the last few months. So the first important milestone to mention is that in addition to the two LIGO detectors, our colleagues in Italy, well, the detectors in Italy, in Virgo, they began operation in early August. And the crucial advantage that gives us is the ability to better triangulate the direction from which gravitational waves are coming. And it also gives you another way to validate the detection. So, we call this our second observing data-taking period, and Virgo joined that second observation run in 1st of August. And just a few weeks later, we got another black hole binary that we detected, this one down here, and notice how much smaller the sky localization is compared with those big bananas that we referred to before. Another pair of black holes. You might say, oh, not another one. But again, the real story here, the emerging story, was the much enhanced ability to work out from which direction the gravitational waves had come. And the real payoff for that improved localization would come just a few days later. Because on August 17th, a quite remarkable chain of events unfolded. So let me very quickly try and take you through that. Firstly, and this is really not doing it justice because there's a whole story to be told about how in the end we produced a plot like this, because there was major issues that had to be addressed by people working round the clock. But basically what you see here is a kind of partly cleaned up version of the data that represents a very strong signal that we believed came from a pair of neutron stars merging. So not so massive as black holes, but still producing this intense burst of gravitational waves that produces this chirp-like upward sweep. All of that, 2 months later, led to the publication of, in fact, a series of papers, but this is just the one that refers to the gravitational wave discovery. And I believe even within about a week, it had become the third most downloaded physical review letter paper of all time. So again, a really big splash. And if you remember those funny looking plots with the black hole masses, the main thing just to stress here is how much more tightly we're able to constrain the combination of masses, a particular combination we call the chirp mass, to do with these less massive systems, these neutron stars. Again, there's lots of detail I'm skating over. Apologies for that, but I do want to show you this because it's so cool. One of our LIGO colleagues, Ben Farr, put this together. So what we're going to see is a little sort of vignette of the different sources. And again, we've got all of our black holes lined up there, black hole binaries. But now what we're going to see is our neutron star event. And in the course of the next minute or so, the signal will become apparent. So just while we're waiting for that to happen, again, if you do a kind of family tree now of these black hole mergers, you can see that they span a good range of masses from, as I said, about 10 times the mass of the Sun to close to 80 times the mass of the Sun. And then there's the neutron stars. These are less massive, not quite so extremely warping space-time, but still bizarre objects compared with ordinary stars because they weigh about the same as the Sun, and yet they're about the size of a city like Glasgow or indeed even Portsmouth. A bit smaller than Glasgow, but you know, neutron stars can be even that small. And if you listen very carefully, you can hear. There you go. That little jump at the end was the merger of two neutron stars. Now, what really made this special, however, was the fact that 1.7 seconds after the neutron star merger occurred, there was a little burst of gamma rays, quite a strong burst of gamma rays, in fact, that was picked up by NASA's Fermi satellite. And this tied in with a well-developed theory, beautifully tied in with a well-developed theory that says when two binary neutron stars collide, you can get what's called a short gamma ray burst. Well, we've just seen one. And the story that that tells, we think, is something very much like this. As those neutron stars are orbiting around each other, they distort space-time just like the black holes were doing, and then you get that burst of gamma rays being given off. That's what the Fermi satellite saw. But moreover, the excellent localization that LIGO and Virgo together gave us meant that there was only a few dozen galaxies within that patch of sky that astronomers had to look in to try and find the aftermath of that gamma ray burst. And again, there was a well-developed theory that said what that should be, something called a kilonova. So astronomers had the job of going to look for that kilonova. And sure enough, they found it. Because here's a before and after. This is a fairly nondescript galaxy, one of those little circles in the previous animation. Well, what astronomers found was that a new star had appeared in that galaxy that hadn't been there before. And it was studied intensively by many observatories around the world. So the little yellow pointers show where the gravitational wave observatories are. But then there's all these other optical and indeed radio, and also other parts of the spectrum represented by satellites in orbit. So across the whole electromagnetic spectrum, we were viewing this object, this kilonova that faded from blue to red in just a few days. And moreover, what the theory had suggested quite strongly was that these binary neutron star mergers producing a kilonova had an important role to play in the production of some of the heaviest elements, including gold and platinum. And indeed, the observations made by all of those observatories of this kilonova, this remnant, really helped to reinforce that theoretical story. So it really does look as if merging neutron stars are responsible for the gold in my wedding ring, or if you've got a Rolex watch, the gold in your Rolex watch. If it's a fake Rolex watch, then I'm not sure if the neutron stars are So that's where we are. You know, the story, I'm sorry I'm not really devoting more time to this, it's my own fault for spending so long in those black holes, but in a way, this is just the beginning of an even richer future. So I've not allowed enough time to really cover that. So let me skip a few slides, and maybe you can ask me about that. Let me just mention, though, that this neutron star collision did at least make the front page of the Financial Times. So not as many as 960 newspaper front pages, But maybe it's because of all that gold being produced. That's what it is. Skip that one to save time. There's a number of really fascinating physics questions that these observations can now address, like, for example, the question of whether gravitational waves in light do travel at the same speed. Our latest results would rather suggest that to an extremely high level of precision, about 1 part in 10 to the 15, the answer is very emphatically yes. And then, well, where do we go from here? We've got tons more work to do, just publishing more papers on this event, but there's more to come. There's other detectors either under construction or under development, which will give us better ability to localize objects on the sky. And then, mapping out over the next few years, we'll be able to see objects at greater and greater distances. And then looking even further ahead, there's plans to build more ambitious and yet more sensitive detectors, either on the ground or indeed moving to other parts of the gravitational wave spectrum, putting the detectors in space. So there's opportunities to see merging galaxies that produce perhaps merging supermassive black holes at their centre, and the gravitational waves from that can be detected not by this. This is a precursor satellite that was testing out some of the technology, but was fantastically successful. It's called LISA Pathfinder. So what would detect the gravitational waves is LISA, which is going to hopefully fly, we think, in about 17 years, 2034. So a while to wait, but lots and lots of good stuff to come. So if you want to find out more about all this, there's the web page I mentioned. We also have our own YouTube channel. We've got Facebook, of course. You can follow us on that, or Twitter. Very happy to answer questions you have now, but if you have more questions for us, you can even just send an email to ligo.org. Who knows, you might answer. You might even get an answer from a Nobel Prize winner. And then, let me just leave you with what I like to call our next spiral toast. We first came up with this idea for the black hole discovery, but I think it's even more apt for the neutron star collisions, given the golden colour of the liquid that we're drinking. I can assure you that it gets harder to do the spiral toast. I can highly recommend it all the same. And I hope I've convinced you that gravitational wave astronomy has got a very bright future. And sorry for running over a little. Thank you very much. Bring the lights up a little bit so I can see you all better and you can see me. A few questions. Really loud so that everyone can hear the question. Yeah, just so that everyone can hear the question.
Slight spectrum wobble nearby stars.
What are you referring to there? Are you meaning that the gravitational waves from those stars, or are you referring to other astrophysical phenomena that would manifest themselves as? Well, other telescopes are very, very good at detecting those signals, but LIGO is not your instrument of choice to do that. Firstly, because those stars, they do show that wobble, but the gravitational waves produced by that wobble are absolutely minute, and moreover, those stars are also rather far away. So even though we've detected gravitational waves from very, very distant sources, it's because those sources are shaking space-time so violently that the signals are strong enough for us to detect. So the wobbling of another star is really important if you want to, for example, detect the presence of an unseen planet. And there are very good ways that we've developed to try and do that. But LIGO wouldn't be the instrument to make those measurements with. You would use conventional optical or infrared telescopes and look for the spectral wobble, which is exactly what you're referring to. So, if we improve our sensitivity to the position of stars well enough, then in principle, as gravitational waves produced by other sources wash over those stars, then we might be able to detect those wobbles. And in fact, if I just go back a couple of slides, Another way to try and detect gravitational waves is using a particular type of star called a pulsar in more or less that manner. Because the pulsars are sending out radio pulses, and if a gravitational wave passed by the pulsars in our galaxy, then it would cause those radio pulses to be distorted. And one might be able to reconstruct the presence of the gravitational waves from looking at that pattern of distortion. Thank you.
Gravitational waves can see right back to the very early 300,000 years of the universe. So what kind of questions might gravitational waves be able to answer?
Well, actually, they can see much further back than 300,000 years. But nonetheless, the great challenge, just like it was for LIGO, is to detect the signal coming from that very early phase in the universe amidst a lot of other competing effects that we might call noise again. So the questions we'd like to answer are whether the universe underwent a rapid period of expansion that we call inflation. And if inflation occurred, and there's a lot of circumstantial evidence that says inflation did occur, then it should have produced a background of gravitational waves in the very earliest moments after the Big Bang. Now, what we don't get the chance to see in light is what was going on that far back because of the period you alluded to, which is about 380,000 years after the Big Bang, that we call the cosmic background radiation. That's like a wall of fog that prevents us from seeing any further back. But the gravitational wave signal from those very earliest moments, in principle, can pierce that fog, or at least can leave an imprint on that fog that we might be able to detect. And indeed, a few years ago, we thought we had, not me personally, but other scientists thought they detected signatures of that background. So again, to summarize, the key question that we want to address is what the universe was doing in those earliest moments. Did it undergo that period of inflation? By measuring and characterizing the pattern of what we call those primordial gravitational waves, we could hope to answer that question. But it's really, really hard. And indeed, the claimed discovery in 2014 turned out there was another explanation. And that's at least, I think, in part why we were so cautious when it came to our turn in 2015, wanting to be really, really sure that we'd made a definitive detection. Thank you. Great question. Yeah.
I wonder, at a point in space which is somewhat removed from the origin of the gravitational waves, but still close enough to be to experience significant amplitude of the gravitational waves, is there a possibility that those gravitational waves could disrupt the nuclei of atoms? And if so, would that not give rise to an electromagnetic signature in a much bigger area?
Well, it's a good question, but I think one must think carefully about what you mean by significant amplitude. Even if the two black holes that we saw in 2015 producing gravitational waves, even if they were as far away from us as the Earth is from the Sun, then the distortion produced at that distance would only be about a nanometer, a billionth of a meter. So you've got to be very, very close indeed. Now, the conventional wisdom is it's a bad idea to get close to black holes. And believe me, it is. But it's not really, in a sense, the gravitational waves that are the problem. So think of the gravitational waves as a ripple on the curvature of space-time. But the curvature of space-time is already massive when you get close to a black hole, or at least a stellar mass black hole, which is where you get this idea, so I've often talked about a lot in sci-fi as well, of what's called, very technical terms, spaghettification, because the gravity on your feet is so much greater than the gravity on your head. So it's that curvature that does for you close to a black hole. It's not the change in the curvature which produces the gravitational wave. So I know I'm not really directly answering the question, but again, the kind of extrapolation from my answer is that if you did want to consider what kind of effects would actually be capable of tearing atoms apart, you'd really need to be looking on way smaller scales than LIGO is probing, and that corresponds in a sense to frequencies that are very, very much higher than LIGO is probing. And I think a loose analogy here that works quite well for me is to think of the fact that with light, for a long, long time we were perfectly happy to think of radio waves as waves. But it was only when we started to look at the much higher frequency forms of light that we realised, wait a minute, we need to think of it as packets of energy, as quanta. So quantum gravity will, we figure, kick in at some point in the sense that all fields seem to be quantized in the universe. But we're not probing those scales, or at least not directly, in the way that, for example, in the early 20th century, people were already probing with light scales that made the quantum description vitally important. And indeed, you could have packets of light energy kicking electrons out of atoms. But we're not probing those kind of energy scales with gravitational waves. So again, sorry, a rather rambling answer, but you know, in a sense, it's all tied up with that idea that I began with about how stiff space-time is. So, you know, it makes it really hard to detect gravitational waves. It also, in a sense, makes it really hard to imagine as being able to kind of harness gravitational wave energy in kind of the manner you're describing. Believe me, if we could, then you'd have, you know, hoverboards, anti-gravity, you know, the full 9 yards, but it might be that that will never be possible. Yeah. Thank you. I'll try and give shorter answers. One last one, indeed, yeah. Very happy to just chat informally to people. Let me get someone from the back, because I was neglecting the back before.
Professor Hendry, you were saying that space-time is very stiff.
Yeah.
What sort of energy is required to give it the ripple that we can then detect? I mean, obviously you're saying combination of black holes. Can you give us a sense of the energy?
Sure, yeah. I mean, indeed, you can do the calculation for yourself. So the amount of energy needed to significantly change the curvature of space-time is what we call the rest mass energy, corresponding to several times the mass of the Sun. So E equals mc squared. That's kind of all we really need. The Sun is, let me get the number right, 2 times 10 to the 30 kilograms. That's 2 million bags of sugar. That's how much mass there is in the Sun. And then the speed of light is 300,000 kilometers per second, 3 times 10 to the 8 meters per second. You've got to square that and then multiply that by the 2 times 10 to the 30. That's how many joules of energy are kind of locked up in space-time. You know, it's just giving a sense of the scale of the energy that's locked up in space-time. And that's why, as I said at the beginning, me shaking my fist isn't going to cut mustard. Yeah.
Thank you.
Thank you very much, Professor Hendry. Good round of applause. Next month he's talking about the making sense of sound, so it's an acoustics talk next month. For those of you who'd like some more astronomy and possibly some beer, just to remind you that the Astronomy on Tap event at the Fox Pub will be next Wednesday at 7:15 p.m. I've got some posts at the front. I'd also like to thank, because I forgot to at the beginning, the IOP South Central branch, also co-hosting this event with us. There's some information at the front, including some freebies for those of you at the back. Thank the speaker. I'd like to thank you for coming, and thank the speaker once again.